Typically, as browser users, we are looking for performance. We want the web to be fast. We're looking for security. We don't want our credit card numbers to leak. And in some cases, we're looking for privacy, as we don't want the web browser to share information about us that we specifically want to keep secret. Welcome to the Technical Marketing Handbook, a podcast all about the technologies, incentives, and mental models underlying the world of digital marketing. In today's episode, we're going to be talking about web browsers, so stick around and enjoy the show. Welcome to another episode of the Technical Marketing Handbook podcast. My name is Simo Ahava. I'm the host of this podcast, and I'm also the co-founder of Simmer, the company that sponsors this podcast. This episode is the first, hopefully out of many, where I do not have a guest, so it's just me and you this time around. Every now and then I feel like I need to unload something off my chest or off my brain, and for that I need an episode all to myself. In this episode, I was wondering what would be the best way to start off the solo content with. And every single thing that I thought up, every single thing that related to technical marketing always came back to the nexus of the web browser. The web browser is such a fundamental and central concept in almost everything we do in digital marketing, in digital analytics, in digital advertising, that it really deserves its own run-through. In this episode, I am going to try to do a very ambitious thing, which most likely will fail miserably, but hopefully you'll get something out of it. And this ambitious thing relates to an interview question that I've always been excited to ask whenever I have the privilege of interviewing candidates for a digital analytics or a digital marketing role. And the question sounds very simple. The question is, what happens when you type a web address or a URL into the browser's address bar and press enter? Now, this sounds like a simple question. You type the URL and then you visit a web page. But it hides so much complexity beneath the layer of the keyboard and the address bar. And it's important to explore this complexity because it has implications on almost everything we do in the digital world. So in this episode, I am going to walk you through the process of what happens when you type a web address into the browser's address bar and press enter. Now, there are some caveats here. First of all, we're going to skip the technical minutiae of translating keyboard presses into digital signals, for example. We don't care about how the machine language works beneath the layer of the user interface. So we're also going to take for granted how these key presses operate the web browser's user interface. And we're going to be primarily interested in what happens within the browser itself and in the client-server architecture of the web. We're also not going to focus on how different browsers and browser engines might handle things, as this is really going to just be an overview of the render process, and we can't get stuck in the trenches going over every single piece of detail with care and deliberation. You're going to be very dissatisfied with my walkthrough in some cases because I'm going to gloss over things that you find very important. You might get bored because I'm going to focus on things that you might find completely irrelevant. I just hope you stick around to the end because all parts of this process are relevant to what we do in digital marketing and digital analytics, and especially in the context of technical marketing. Before we head on over to the walkthrough, it's time for a hopefully familiar by now message from our sponsor.
Are you a marketing or a data professional looking to skill up? Take a look at the online courses Simmer has to offer at teamsimmer.com. The courses are completely self-paced and your enrollment will grant you lifetime access to the material, including any updates. Go to teamsimmer.com and use the coupon code HANDBOOK to get 10% off your course purchase. That's teamsimmer.com.
When we type a URL, let's use www.google.com as an example. When we type a URL with a name like that into the browser's address bar and press enter, what we are actually interacting with is the domain name system. The URLs we use are like entries in an address book. So when we type www.google.com, we are instructing the web browser to fetch for us some resource that hopefully exists at the end of this address. But the server with which our browser is interacting with when we do this request is not behind a domain name. The server is a machine operating in the internet, and it's been assigned an IP address, an Internet Protocol address, which is a bunch of numbers that tries to uniquely identify each machine on the web. But because it would be very difficult to browse the web if we always had to remember the IP addresses, we need a domain system instead, as it's much easier to remember www.google.com than it is to remember 142.250.74.100, which is the IP address of google.com. So the domain name system, the DNS of the web and of the internet, maps human-readable addresses to IP addresses. And that's why we can browse with www.google.com, and the web server at the end of it will know that the request was for this particular resource. So when you type www.google.com into the address bar, the browser starts a process of DNS resolution. So this applies only to the domain name itself, the google.com part, not the IP address. There are actually many different name servers in the internet, and each is responsible for some part of this domain name you want to access. And the resolution is done recursively, so the domain name maps to an IP address in a pattern starting from the most generic domain name and moving to the most specific one. And this is read from right to left. So with www.google.com, the first domain name that is resolved is the .com name. And the .com is actually mapped to a server or a domain name system, which will then look at the next part of the domain name, which is Google, so as google.com. And there's another machine or another domain name system that has details about the google.com space. And this machine then finally looks at www prefix and resolves this final part of this domain name, and the IP address matching this is communicated back to the browser. All of these different domain name servers are interacting in this way, and this can be a fairly time-consuming process if this recursive mapping needs to be done every single time you want to resolve an address, because these domain name servers are located geographically in diverse places, and the network requests and signals might need to traverse long distances to actually get the job done. And that's why there are caches all over the place. Cache spelled as C-A-C-H-E. So before this recursive search even starts, the browser looks actually into 4 different caches to see if the domain name has already been resolved and stored temporarily. There's the browser's own DNS cache. There's the operating system's own DNS cache. Your web router, the router machine you use, has a DNS cache. And finally, the internet service provider that you're using might have a DNS cache as well. The purpose of all these caches is to preserve time and resources by temporarily storing information that could be reused. And the domain name is one such piece of information. So instead of having to go through this recursive resolution using all these different domain name servers, if www.google.com is found in one of these caches, then this recursive step doesn't need to be done at all. Instead, the cache simply returns that, hey, we remember google.com is mapped to this and this IP address, and this is then returned back to the browser, and it's much faster and preserves a lot more resources than if you had to go through the domain name servers themselves. So I hate using metaphors and analogies, but I'll just make an exception this one time. Think of a cache as your food cabinet. So when you want to make pasta, the first thing you check is if you already have some in your cabinet. And if you do, you can get around to cooking your dish almost instantly. But if you don't have pasta or if it's expired, you need to go to the store to fetch some more. So the cache works as an initial registry that you can look into to see if the work has already been done and stored, and then you can use this stored information. Now, once the browser and the server know that google.com has been resolved to an IP address, the browser initiates something called a TCP/IP handshake. And this is short for Transmission Control Protocol/Internet Protocol. And this is a handshake done between the browser and the target machine. The purpose of this handshake is to establish the protocols and rules for communication between the browser and the server machine. And these rules include a lot of different things, but the key thing is that if both the browser and the server accept these rules, so if the handshake is a success, a transmission connection can be established and data can finally be transmitted between the browser and the server. So this is like an olive branch. It's an initial query between the browser and the server that, hey, is it okay if we communicate? Is everything fine? Is everything secure? Is everything private? Can we go on with this request? So just to recap, at this point, we have the domain name mapped to an IP address, either through the process of DNS resolution using domain name servers or by virtue of finding the mapping in a cache. And the browser has established communications with the server machine that exists behind the IP address. And at this point, the browser can actually make the request. In the request, we have the URL, which in this example is https://www.google.com. The HTTP or HTTPS in front of the URL establish the protocol for transmitting the request data. HTTP is short for Hypertext Transfer Protocol, and HTTPS adds the word secure to the end. Most of the web content that we interact with is in hypertext and is using something called HTML, which is a hypertext markup language. And hypertext refers to the process of linking documents together and for adding metadata by virtue of tags and so on. There are other protocols as well, such as the File Transfer Protocol, which is abbreviated to FTP, but HTTP and HTTPS are the main means of communications for web content. Now, if you're using HTTPS, as you should, there is an additional step of verifying that the security of the website has been appropriately certified by means of something called an SSL/TSL handshake. Most of the web pages online today use HTTPS, and while it doesn't guarantee any type of real security, it is a very strong signal, and it does encrypt bits and pieces of information, making it difficult to initiate man-in-the-middle attacks or to hijack those content streams. If a page is not served with HTTPS, but only with HTTP, you should be very, very careful when interacting with the page. Do not add any form content. Do not share your credit card details. Do not make purchases unless the site has been certified with an HTTPS certificate. Browsers today will indicate if the HTTP certificate itself is invalid or expired, but even that doesn't prevent potential misuse. Now, once everything checks out, once all of these handshakes are complete, once the browser and the server are ready to communicate fully, the web server finally receives the HTTP request. Every single URL, if resolved to an IP address, will be forwarded to some type of a server machine. A server machine's purpose is to react and respond to requests that it receives, manipulate or parse them in some way, and then send a response back to whatever source sent that request in the first place. With HTTP content, such as when requesting a web page, the web server is typically quite a simple piece of machinery, as its only purpose is to make sure that for whatever resource was being requested, an appropriate response can be given. Obviously, the browser user hopes that the request is a successful one and returns a web page in the response body. But before we go too far, the request itself includes more than just the URL of the resource that the browser wants to fetch. So even though we are simply asking, please send us a web page behind www.google.com, the request itself actually introduces a method which indicates what type of a request it is. When you type a URL into the address bar of the browser, it initiates something called a GET request. But web servers can also serve POST requests, PUT requests, delete requests, and other keywords too. The method is used as a guideline for the web server to do something. So even though you could use a GET request to make a change in a database in the web server, for example, this is extremely discouraged because the GET request can't be adequately protected with things like authentication or API keys. And in these cases, you would typically be instructed to use a POST request or a PUT request instead to make sure that the request is authenticated so that no random person out there could simply make changes to your database. In addition to the URL being requested and the method, the request also includes headers and sometimes a body. Now, one of the most significant headers in the request is the cookie header, which includes all the cookies written on the site the request is sent to. So when you want to browse to www.google.com, the request will include any cookies written on google.com or www.google.com. Cookies are small files that comprise a name, a value, an expiration, and sometimes some other flags too. Especially in the context of privacy, there's a distinction being made between some so-called first-party cookies and so-called third-party cookies. But this is a bit of a misnomer, as cookies themselves are never classified as such. There's just cookies. A cookie itself has no information about whether it's a first-party or third-party cookie. The cookie is always the same. What matters is the context of the request. When you navigate to a website, you are operating in a first-party context with the URL you wanted to navigate to. Thus, any cookies included in the request are accessed in a first-party context. But when you are on google.com, for example, and the browser needs to fetch something from doubleclick.net, this is no longer a first-party same-site request, because the site to which the request is sent, doubleclick.net, is different from the site the user is currently on, google.com. In this case, the doubleclick.net cookies included in the request are accessed in a third-party context. And many browsers block or suppress access to cookies in a third-party context. Now, if such a browser is being used, then the request to doubleclick.net while on google.com would not include any cookies. In any case, when the server receives the request from the browser, it will then run some processes to produce the resource the URL is pointing to. Now, there are many different ways for the server to do this, with some type of a template engine being the most popular one. So instead of having every single possible file stored as static files in the file system of the server uses some dynamic programming language, such as PHP or .NET or JavaScript, to dynamically create the resource using template files. Now, whatever the means, either the server finds a resource or it doesn't. If it finds a resource, it responds back to the browser with it, typically with a status code of 200. If it doesn't find a resource, it typically returns a status code of 404, and possibly a page not found resource to go along with it. Status codes are a shorthand for the server to communicate information in a very condensed format. The 200 status code is hopefully the most common one you'll encounter, as it's a generic code for OK, the request was a success. Codes starting with 3, such as 301 or 302, indicate that the server wants to actually redirect the user to some other resource instead of the one they asked for. Codes that start with 4, such as 403 or 404, have to do with some type of error in the request itself, such as the request was not authenticated or the request was for a resource that doesn't actually exist. And status codes that start with 5, such as 500, are typically reserved for internal server errors, so something went wrong in the server itself, and it's often not because of something the client or browser did. When the server returns the resource to the browser with a status code of 200, it is returned as HTML, which is short for Hypertext Markup Language. It's a set of instructions for the browser on how to build a dynamic web page with the content provided by the server. And before we move on, let's quickly recap. At this point, the browser has made the request to the server, and it uses a protocol such as HTTP or HTTPS to send the request with. The protocol is used to establish certain rules for the communication between the client machine and the server machine. The request itself includes more than just the URL. It includes a keyword such as get, and it also includes headers and sometimes a body. The cookie header is one of the most significant headers because it is often used as a vector for tracking, for privacy, but also for persisting information such as shopping carts or user logging from one page to the next. The server, once it receives the request, will then try to find a resource that matches the request and return it back to the browser. If such a resource is found, it is returned, and as the request was for a URL or a web page, the response contains an HTML file in the response body. So we are now here with the web browser that has just received a response back from the web server with an HTML file that corresponds with www.google.com. The browser next starts following the instructions in the HTML file, starting from the very top, the very first row in the file, and moving row by row until it reaches the end. When the browser starts rendering the HTML file into a dynamic web page, it actually comprises a couple of different branches. The first is converting the HTML elements themselves into a dynamic model called the document object model. And this includes all the elements or HTML tags that describe the content. It includes all the characters, all the tokens, and everything else that comprise the web page itself. And these are all aligned into a tree format. So if there's an element that contains other elements, such as a div or a box that contains text, then the latter is embedded in the first in the tree model. So we get this branching tree that starts from the very top, the HTML node itself, moves through the body, has these different elements, and so on. Now, the other part of the render process is styling. Styles are typically included in a style sheet, a cascading style sheet, shortened as CSS. And CSS includes instructions for how to align elements, how to paint them, what types of fonts to use, and so on. Similar to the document object model, the browser turns the raw CSS instructions into an object model as well, known as the CSSOM, or the CSS object model. The render tree now has two different structures. One is the DOM and one is the CSSOM. So one is the element representation and the web page document itself, and the other are the styles associated with the first. And when these are combined, they are combined into a render tree. And the next step is to lay out this tree into the kind of thing that you end up seeing on the web page. And what the browser has to do is it has to calculate the size, alignment, and position of everything on the page. So it creates a framework or a blueprint for how elements are aligned on the page and how they appear in the browser viewport or the visible part of the screen. This is sometimes called the reflow step, and it basically establishes the layout of the page. Once the position of every element is computed, the next step is to paint the elements on the screen, and this is called the paint step. So with the information in the document object model and in the CSS object model, and with the exact layout of the elements having been computed in the reflow step, the browser then proceeds to paint every single individual node on the screen. And this is the point where you start actually seeing items appear on the web page. And if you have a slow connection or if you have a slow computer, you'll see how it happens one by one rather than being blasted in a finalized state on the screen itself. This is the process of converting the HTML file and the instructions within into a living web page. An important aspect of this render process is that the browser runs a single execution thread. This means, in a very abstract way, that it can only ever execute one render task at a time. Thus, when the browser encounters a particularly resource-heavy instruction, such as the download of a huge image or a long, complicated script, everything else in the HTML file needs to wait for this process to complete. And this is called blocking, and it's a major problem with web pages. To mitigate blocking, the HTML can instruct the browser to perform some tasks, such as downloads, asynchronously. Asynchronous means that the download is initiated, but rather than wait for it to complete, the browser continues rendering the next row in the HTML instruction and to turn it into a web page. Once the download is completed, the browser does whatever needs to be done with the asynchronously downloaded resource. This way, large files can be downloaded in the background without this download process interrupting the rest of the render process. The HTML file itself contains a lot of metadata in addition to the content itself. The most common pieces of metadata are the page title, which is rendered to appear in the browser top bar or in the tab name, and the page meta description, which is often used by search engines to gain additional insight into the search engine results page. There might also be additional metadata for search engines as well as for social media platforms so that they can render preview images and descriptions correctly. If the browser encounters scripts or images in the HTML, then it needs to initiate a new request-response process with whatever server is at the end of the script or image resource respectively. So every single image that the browser needs to download, it needs to go through the entire process described in the previous 25 minutes again and again and again. Thus, to render a single web page, the browser typically has to send dozens upon dozens of HTTP requests. And this can be very problematic for bandwidth and for computation power if there are hundreds of requests to go through for any given page load. But essentially, what the browser is doing with the HTML instructions is it's trying to create a dynamic representation, which is the web page that you see once the page has rendered and loaded. Being a dynamic representation, it means that the web page can be accessed and manipulated with the scripting language of the web, JavaScript. But rendering a poorly constructed HTML instruction can also really shine light on how different browsers can be in terms of how they align all the elements. Now, something might look completely fine in Google Chrome, but it can also be a complete mess in Safari. And that's why web standards are so important, as they establish common parameters for how to render the HTML, among other things. As I mentioned in the beginning, this was a very abstracted description of the process. There are many things I glossed over, such as how the initial request handshakes work, how all the different caches are implemented, what the relationship between a browser and its browser engine is, how the web server can further manipulate the response, and so on. But that's okay. There are plenty of podcast episodes to come to explore some of these more obscure details. What matters at this point is understanding the relationship between the browser, which functions as the client in this case, and the web server to which the client sends those requests. There are certain security and trust signals all over the place, such as when you type a URL, you're typically looking for something behind google.com, but an attacker could surreptitiously have you copy paste a URL with some hidden symbols, or maybe one of the letters is just a little bit different encoding, in which case you'll actually be requesting some other resource, but you didn't think of this because you thought you were going for google.com. The relationship between the web page and the HTML being downloaded from the server is another source of contention. The way the page is rendered, as already mentioned, can change from one browser to the next, but also how the page can be manipulated, how information can be pulled from the page and combined with things like cookies to make analytics and advertising more detailed. That can differ a lot too between different browsers. Typically, as browser users, we are looking for performance. We want the web to be fast. We're looking for security. We don't want our credit card numbers to leak. And in some cases, we're looking for privacy, as we don't want the web browser to share information about us that we specifically want to keep secret. This last part about privacy is, again, very contentious, because there are many cases where we might want to compromise our privacy to get something in return. And for some, this means opting in to targeted advertising in order to receive more relevant ads, opting into first-party data collection to allow the site to see what you're doing so that they can improve your experience, opting into A/B testing, and so on. Obviously, not many websites have an opt-in mechanism, and instead they'll just track you as much as they like. And this is one of the reasons that many browsers today implement some sort of tracking protection mechanism. And even though these tracking protection mechanisms started as a way to prevent the browser from being misused for collecting data from the user, some of these tracking mechanisms are leaking into other parts of this client-server architecture. For example, a browser such as Safari is looking into the domain names that you are trying to browse to, and in case it finds that there are domain names in that resolution chain that are not first party to what was actually being requested, Safari suppresses some cookie information that would otherwise be sent. And similarly, some of the caches that can be misused to track you across the web are being partitioned by browsers to make sure that information that happens in one page cannot be used on another page of the web. And this is one of the points that I did gloss over kind of intentionally, but it's good to understand that the web is a fairly stateless thing. Anything that happens on a single web page is erased by the time the user unloads the page because they're navigating to another page or closing the browser. It is with cookies, with servers, with other browser storage that the relationship between one page and the next can somehow be united. And that's why when you log into a web page and you stay logged in when moving to another web page, this persistence works. Your login information is stored in a cookie. And this is also why cookies can be problematic, because when the vendor knows on which pages you visit, they can extrapolate information from your behavior that you might have wanted to keep secret. But that's the topic for another podcast episode, and privacy is already something that we have talked about at length in previous interviews. It's time to wrap up this podcast episode. Thank you so much for your patience and for sticking all the way to the end. I hope you have gained some new understanding of how the relationship between the web browser and the web server is built. And I hope that you are also thirsty for more information, because I definitely will provide more details about this process in future podcast episodes. Until then, take care, stay safe, keep browsing the web, and see you in a couple of weeks' time with the next podcast episode.